Hello everyone, my name is Yashaswini, currently pursuing BE in Sri Venkateshwara College of Engineering. In this video, we are going to learn about graph searching algorithms from the subject called Design and Analysis of an Algorithm. Graph searching. Graph searching is a fundamental algorithmic technique used in computer science for solving many problems, including pathfinding, social network analysis, and natural language processing. Types of graph searching algorithm. There are different types of graph searching algorithms with its own strengths and weaknesses. Some of them are DFS, which stands for Depth First Search, which finds a path through the graph by exploring each branch as far as possible before backtracking. And then BFS, which stands for Breadth First Search, which explores all the vertices at the same level before moving on to a next level. Dijkstra's algorithm, which finds the shortest path between 2 points in a weighted graph. A-star algorithm, which estimates the cost of the remaining path using a function to find the shortest path to a goal node. Coming to the first type of graph searching algorithm, that is DFS. DFS is a classic algorithm for solving problems on trees or graphs. It can help finding a connected component or cycle in an undirected graph or a topological sort of a graph. It's simple but can easily get stuck in an infinite loop. We have three steps. The first step is start at the root node. In DFS, we start at the root node and mark it as a visited. The step two is explore each branch. We explore each branch as far as possible before backtracking. The step three is backtrack. If we reach a dead end or a node that has already been visited, we backtrack until we find the new unexplored node. Coming to the second type of graph searching algorithm, that is BFS, which stands for Breadth First Search. BFS is another classic algorithm used to search in graphs or trees. It is useful for finding the shortest path between two nodes or for finding all the nodes at a given level. It is easy to implement but requires more memory than DFS. We have traversal order and optimal pathfinding in BFS. Coming to the traversal order. In traversal order, BFS travels the graph level by level from the starting node to the destination node. Coming to the optimal pathfinding, BFS always finds the shortest path between two nodes, giving the nickname of breadth first shortest path algorithm. Dijkstra's algorithm. Dijkstra's algorithm is a weighted algorithm used to find the shortest path between two nodes in a graph. It works in a greedy manner, always selecting the node with the lowest distance to process next. It can also be used to find the shortest path to all nodes in a graph through a process called label correcting. We have four steps. The first step is setup. Start by assigning the starting node a distance of 0 and all other nodes with a distance of infinity. Step 2, select the node. Select the unvisited node with the lowest distance. Calculate the tentative distances to its neighbors. Step 3 is mark the node. Mark the current node as visited and update the distance of its neighbors if the tentative distance is lower than the current distance. Step 4 is repeat. Repeat steps 2 and 3 until all nodes have been visited or the destination node has been marked. A-star algorithm. A-star algorithm is a heuristic search algorithm that estimates the cost of the remaining path using a heuristic function that combines the cost of the path already taken and the estimated cost to the goal. This makes it more efficient than other algorithms like Dijkstra's, especially for large graphs. We have admissible heuristics and consistent heuristics. Coming to the admissible heuristics, for the A-star algorithm to work correctly, the heuristic function must be admissible, meaning it never overestimates the cost to reach the goal. And then The consistent heuristics. A consistent heuristics is one of that satisfies the triangle inequality, meaning that the estimated cost to the goal of a node is never greater than the actual cost of reaching a neighbor plus the estimated cost to the goal of a neighbor. In this slide, we are going to see the comparison of algorithms like DFS, BFS, Dijkstra's, and A-star algorithms. Each algorithm has its own strengths and weaknesses. The best algorithm to use depends on the characteristics of the graph, the structure of the problem, and the efficiency requirements. Here is a comparison of some important features like time complexity, space complexity, optimality, and search space size. For DFS, the time complexity is O into V plus E, where V is the number of vertices and E is the number of edges. And then the time complexity of BFS is O into V plus E. Dijkstra's algorithm time complexity is O into E plus V log V, and the time complexity of A star is O into E, which stands for number of edges. Now we are going to see about the applications. Graph searching techniques are widely used in a number of fields. For example, they can help identify social influences in a network or optimize the distribution of goods in a logistic network. We have social network and then logistic networks. In social networks, graph searching algorithm can be used to detect communities, influencers, and opinion leader in social networks. Logistics. These techniques help optimize delivery routes, reduce transportation costs, and minimize transit time. Now we will see some advantages of graph searching algorithm. Coming to the first advantage, it is efficient in pathfinding. Graph searching algorithms can efficiently find paths between nodes in a graph. BFS guarantees the shortest path in an unweighted graph, while DFS can be adapted for various pathfinding objectives. Coming to the second advantage is memory efficiency. Unlike algorithms like Dijkstra's that require maintaining a priority queue, graph searching algorithms often have lower memory requirements. This makes them suitable for memory constrained environments. Coming to the third advantage, which is simplicity. Graph searching algorithms are relatively simple to implement and understand. They are a good starting point for grasping the basics of graph traversal and manipulation. Coming to the fourth advantage, that is space complexity. In cases where the solution lies deep in the graph, DFS typically has a lower space complexity compared to BFS. This can be advantageous when dealing with deep graphs. Coming to the fifth advantage, which is topological sorting. DFS can be used to perform topological sorting of directed acyclic graphs, which is valuable in scheduling tasks with dependencies and representing partial orders. Coming to the sixth advantage, which is game tree search. DFS is a core component in searching game trees in board games. It helps explore possible moves and states, contributing to the AI's decision making process. This is all about the graph searching algorithms. I hope the video was informative for you all. Thank you for watching.